Okay, I think we can start. So, welcome everybody to today's session of the Newton 1665 seminars dedicated to the strong CP problem. We're going to have three talks on different aspects of the problem. The first one by Bjorn Garbrecht will be on technical aspects that, if they turn out to be true, would imply the absence altogether of the strong CP problem. The second talk is by Claudio Bonatti and will be on recent lattice developments of the problem in relation to the theta dependence of the QCD vacuum. The third talk by Marco Gorghetto will be on very recent results that suggest a very large contribution of cosmic strings to the axial relic density, much larger than was thought before. Well, given the strong claims of these talks, in particular the first one, I would anticipate and encourage a quite long discussion. So I would ask the speakers to stay sharply on time. And finally, let me add a personal comment before starting. Well, these bad times, as a side effect, give us the opportunity to have several experts on a topic virtually on the same place. So let's try to take the good out of this, and especially because of the strong claims, let's try to have a discussion that allows the community to understand what's going on. So I think we can start. So Bjorn, please start the sharing and the stage is yours.
Yeah, okay. So thank you, Daniele, and the other organizers for putting this event together today. The title of the talk is Absence of CP Violation in the Strong Interactions. And this is work that I have carried out with Bjorn I, Juan Cruz, and Carlos Tamarit. Now here's the outline. I will first specify the CP-odd Lagrangian terms that we are dealing with, and these CP-odd Lagrangian terms lead to correlation functions, and from these correlations, one can infer effective operators. Now correlations are calculated from Green's functions, and I will also talk a bit about Green's functions for fermions in the background of n instantons and n bar anti-instantons. So to finally arrive at the correlations, we need to calculate certain well-known interferences in this case. That is, we need to sum over the number of instantons and anti-instantons. We need to integrate over the locations, and we need to integrate out other collective coordinates. And then we arrive at the correlation functions. So to this end, my discussion does not deviate from anything that would leave to the standard results. And so the decisive step comes into the game when we interfere among different topological sectors. So what we are saying is that these interferences among the different sectors are immaterial, provided you carry these out in infinite spacetime volume. Whereas, and I will also discuss that, if you carry out these interferences in finite spacetime volumes, you can compute the CP violating correlations. Now, these CP-odd terms that we are talking about are, of course, here hidden in the mass term and in the theta term or topological term. So in the mass term, of course, the sign part of this exponential is CP-odd. We can carry out chiral field redefinitions, which transform alpha and theta, but there's a rephasing invariant, which is called often theta bar, which is the sum of this theta plus the sum of all the quark phases. The instanton effects then can be described in terms of an effective vertex, which includes all flavors and F flavors of fermions. But you also see here that the structure again is chiral symmetry violating, just as the mass term here. And in general, there is a CP phase. Now the key question is, what is the phase psi? And the standard calculations predict that this phase psi here should be set or be identified in this parametrization with theta. And then in general, there's no relation between theta and alpha, and you would expect CP violation just from the misalignment of these two operators. In this talk, we claim that when we calculate the correlation functions, we come to conclude that psi equals minus alpha, and in this case, then there would be no CP violation because there's an alignment. One should note that both of these options comply with theta bar being the only CP the only rephasing invariant CP phase, because clearly this phase everything depends on in the first case is just theta bar, whereas in the second case there is no phase. So this both complies with this general argument. Now, this effective vertex is chosen such that it generates the following correlation functions at tree level. So here we have correlations that come from substituting fermion propagators into the vertex. And here again, we have this chiral symmetry breaking and for psi not equal 0 CP violating structure. And these correlations with the structure should be compared with the leading contribution to the two-point function. So we are thinking here of a dilute ensemble of instantons and anti-instantons. And in between these instantons and anti-instantons, the space-time is trivial. And therefore, the leading contribution to the fermion two-point function is given just by the standard Dirac propagator. Whereas, of course, we will receive and we will compute corrections that come from the regions close to the instantons. Now, having specified this leading contribution, we see here that if we write it in the position space representation, that we can also see this phase here. This can be, of course, computed, but it doesn't need to be computed here. The structure is more transparent if we leave it as an integral, of course. And again, we can now look at these correlation functions and make the same inference about the presence of CP violation or no CP violation. So this is sort of the goal of this talk, to calculate these correlation functions and look what these phases here are. Now, from now on, to keep things simple, we set NF equal 1. The general case is treated in our paper for more flavors. Okay, so how do these green functions look like? The Euclidean Green's function satisfies, of course, the following equation here. And in the context of instantons, it is most convenient to calculate this Green's function in terms of a spectral sum. And for the spectral sum, we need to know the eigenfunctions and the eigenvalues. And once we know this eigensystem, we can write down the spectral sum as follows. So there will be discrete contributions as suggested by the sum sign and the continuum as suggested by the integral sign. And when we then act again with the Dirac operator on this equation, these eigenvalues will just cancel. And then when you can cross out the denominator, you're left with the completeness relation, which then just gives the delta function here. Okay. Now, of course, in the massless case, there is a problem because there are, in general, fermion zero modes present in the instanton background. And in particular, we have the winding number, delta n, which is an integer, provided we choose boundary conditions such that the physical gauge fields vanish at the boundaries of the spacetime, or if we have boundary conditions that are periodic. And then for these integer values that we can assume, we know that the difference, or this winding number, equals the difference between the number of right-handed and left-handed zero modes. And it is also well known how these zero modes look like. So there's this chiral structure. For an anti-instanton, it is left-handed by this convention. There's the radius of the instanton. It decays at large distances. And we have here a structure with spinor indices and, in this case, SU2 gauge indices, because we can reduce the general case to an SU2 block of the larger unitary group. Okay, and then one can regulate this problem with the vanishing mass by introducing the mass again at first order in perturbation theory. That is, we regulate the zero mode contribution by including the shift.
Bjorn, can I ask a question?
Yes.
Sorry, this is John Mark Russell here. You know, the one flavor theory is very different in structure from the multi-flavor theory. In particular, it's known that the form of the correlation functions you're computing has different dependence upon the mass. And, you know, because of the anomaly, there is no good definition of what you mean by zero mass. And so why do you believe this one flavor computation captures what's important for multi-flavor QCD?
Yeah, but I think I understand what you mean. You say that in the one flavor theory, these instanton effects directly generate a mass for the fermion.
Yes. In particular, it gives an additive contribution. Yeah. So you have to be very careful. And in particular, it's known from work of Kreutz and other people that there is a difference in the behavior in the one flavor case and the multi-flavor case.
Right, but I think this is not crucial for the conclusions that I'm going to draw, because as I said, we also discuss in the paper the multi-flavor case, and we are not really worried to this end about the dynamical mass generation of the fermions and solving these equations in a self-consistent manner. We are just looking at these first order corrections that are induced by the instanton. And
yeah, okay. Okay. I haven't looked at your paper, so I apologize. But yes, one has to be careful. But fair enough, as long as you're aware of the problem. But
yeah. Okay. So where was I? Okay, here. Okay, so we have regulated this now with the mass term here in this case, and we ignore the mass term, the contribution for the non-zero modes. I would like to point out that one does not have to do this. As long as the massless spectrum is known, one also can construct these tree-level Green's functions in an exact manner without inserting the mass term perturbatively. As we have shown in our paper, the advantage here is that these expressions are simpler and more transparent to deal with. So here's what we take then for the Green's functions in n instanton and bar anti-instanton background in Minkowski space. So we are understanding here as phi as the analytic continuations of the Euclidean zero modes to Minkowski space. And so the approximation here is that for small masses, the zero modes dominate close to the cores of the instantons, far away from the instantons. The solution goes to the zero instanton configuration. I think this is reasonable. You also find this approximation being made in the paper by Diakonov and Petrov from the 1980s, except that they did not track the phases here, these general CP phases that we have here explicitly, and they're, of course, in the expression that I have just showed you. And of course, eventually we want to see, after all interferences, where these phases lead us to, and then we want to compare. There is something here with the analytic continuation from Euclidean to Minkowski space. So these are chiral blocks, diagonal chiral blocks, and in Minkowski space, they would therefore connect left with right, whereas the Euclidean modes here, where they come from, are left and left. So we have been very careful, and there's a bit of a technical discussion in our paper, that these are indeed the correct solutions for the Green's function in Minkowski space. So what we see at this level, that here's the phase alpha and there's the phase alpha, so there's still an alignment between the Lagrangian mass term and the instanton-induced chiral symmetry breaking. So there's no indication of CP violation at this point, but so what? The theta phase has not entered the calculation thus far, so we have to wait and see. Which brings me to the interferences within the topological sectors. So we choose here the theta vacuum in Minkowski spacetime as the sum of these pre-vacua with definite Chern-Simons number. We do not take a phase here because we keep the phase in the topological term or equivalently in the fermion mass, because these options are equivalent. So we show explicitly the phase in the topological term and in the fermion mass, but we're not dealing with three phases here, but you can convince yourself that the answer would be the same. And then this correlation function in this fixed topological sector reads as follows. So we have to fix here in the sum the winding number. And in this step, we perform a saddle point approximation. So we pick a saddle with n instantons and n bar anti-instantons. And then we integrate in small fluctuations about these configurations. And these integrals give us, of course, one loop determinants. So I'm writing here reduced fermion and gauge boson determinants in the instanton background, because we have to pull out, of course, the collective coordinates here. There are combinatorial factors, clearly because of the indistinguishability of the instantons among each other and the anti-instantons. And here are the collective coordinates. So think of these as, for example, dilatational modes and gauge orientation modes. More importantly, there are these translational collective coordinates. So here are the locations of the instantons and of the anti-instantons that we need to integrate over. Here, this is just the Green's function that I've just been talking about in the n instanton and n bar anti-instanton background. Then we have a suppression. SE is the single instanton action to be multiplied in the exponent with the total number of these things. And here we have the total topological phase that's being incurred. So this n minus n bar is just delta n. Okay. The partition function looks the same, except for the fact that we do not have residual integrals over the locations, because we make a dilute instanton gas approximation where these things don't interact. And therefore, it doesn't depend on the location of these objects at this approximation. But again, you have these phases here, exponential suppression, and also these volume terms. Okay, now let's do the last step and integrate over all of the locations in the correlation functions for the fermions. and then we end up with some space-time averaged correlation. So this would depend on the relative coordinate between x and x prime, but not the average. And then we recognize the contribution from instantons and anti-instantons, and of course the chiral symmetry breaking. So again, this expression here, something very similar to this, can be found in this paper by Diakonov and Petrov again. And they also discuss that the sum is dominated by particular values of n, or n bar. And this you can estimate as follows. Oh, sorry, my touchpad is going crazy. No, here. This you can estimate as follows. So choose as alpha everything that is raised here to the power n plus n bar. So this would be these two terms. And then pay attention to kappa here, which essentially is this exponentially suppressed contribution. So you calculate the expectation value of n, and you end up with alpha vt. So this is pleasing because here, 1 power of vt is missing compared to here, and of course also compared to here. Yeah? So if you now take this correlation function and you normalize it by the partition function, the volume, space-time volume dependence drops out. In addition, because there's this factor alpha, which contains this exponential suppression, these contributions are exponentially suppressed, as you would expect. Okay. Next thing you can ask is how wildly are these numbers here fluctuating? And if you take the space-time volume to infinity, well, they are not, the relative fluctuations essentially go to 0. So this means that in the limit that everything, the space-time goes to infinity, these contributions here are all the same. And then you have the same phase here and the same phase here, because this topological phase is multiplying the Lagrangian mass terms and the instanton-induced terms in the same manner. One can also take this a bit further and carry out these sums, and under this restriction that n minus n bar is delta n, and one finds here coefficients in terms of modified Bessel functions that just differ in the index. And as I said, for vt to infinity, they should all be the same, and this can be expressed in terms of this limit here. So if we take the space-time volume to infinity, these Bessel functions do not depend on their index anymore. And so at this level, one can already notice that there might be something, that there's no relative CP phase between the mass and the instanton-induced terms, if one really can forget about these indices. And therefore, there would be an alignment between these phases and no CP violation. But I will carry out these sums explicitly in a moment to make this very clear what is happening. Okay, correspondingly, again, we can calculate the partition function. And here I highlight this factor here. So essentially, what is going to happen is that if we can identify all these modified Bessel functions, and this factor here, when we take the ratio, all these structures here in terms of the modified Bessel functions and this total topological phase cancel between the correlation and the partition function. But I will carry this out in a moment. Okay, here's what I already said. The topological phase is multiplying everything indiscriminately, whether it's a contribution from the Lagrangian mass or from the instantons. Another point I would like to emphasize that is also discussed in the paper is that other correlation functions, such as endpoint functions or the stress energy tensor, can be calculated from Feynman diagrams with the Green's function of interest. That is the fermion correlation or the fermion Green's function in n instanton and n bar instanton background. So once we have calculated this Feynman diagram, then according to the same procedure that I'm just describing, it remains to average over n and n bar, the locations and the remaining collective coordinates. Okay, so let's now come to the decisive step, which I hope I will explain clearly. Now, here's the partition function, and this object here with m, so the inner sum is what we have calculated so far. This is the C sub delta n in the fixed topological background. And now let's finally do the interference over the topological sectors, such that we obtain this object here, that we are using to normalize our fermion correlation function. Now for the fermion correlation function, we do the same thing. So this is what we calculated already. And now we also interfere over the topological sectors. And here's the thing. We take the space-time volume to infinity before we evaluate these topological sectors, because these winding numbers, these Chern-Simons numbers, are defined at boundaries of an infinite space-time. And when we do so, it is precisely happening what I said. We can identify all these factors here, these modified Bessel functions and these phases here, in all of these terms, this one, this one, this one, this one, they all cancel, and we are left with this expression here. This is just a copy of the zero instanton function that I've written down earlier. And here we can directly compare these two phases. They are aligned, and we conclude there's no relative CP phase between the mass and instanton term. So to make clear why we arrive at this conclusion, I look what is happening if we order the limit the other way around, which is how the calculation usually is done. So then we first sum over all delta n as well, which we can achieve by just summing over both n and n bar independently. And then you just recognize here, these are essentially exponential series, two exponential series. And the result is then simply given by this one and for the partition function here. And we see that the factors that are canceling are those, so they are not really of further interest. But now we have here, instead of alpha, we have theta in these chiral structures here. And so the relative phase now is precisely theta bar between these two terms. Okay. This means that there is a relative CP phase, which is theta bar, and this would lead to CP violating observables. However, the order of the limits is not a choice, but as I said, it is dictated by the fact that these theta vector are constructed in infinite volumes at boundaries at t equals plus minus infinity. Okay. Now, of course, it would be annoying if we would have conclusions that would depend on whether the spacetime is finite or infinite. We don't know, we just know it is large. So I would like to spend the last two slides on these cluster decomposition arguments that would also more readily apply to finite volumes. And so this is just the standard argument that you find in Weinberg's book. So consider the expectation value of an operator O in a spacetime volume omega. And there we interfere readily over the different topological sectors. So here in this action as omega, I don't assume any phase, but I want to recover the phase from these weights here, f of delta n. So we assume general weights of f of delta n, and we ask ourselves, how do they have to be chosen such that we have a sensible theory? Well, then we can think of factorizing the path integral into two contributions from two volumes. And we assume that the binding number is additive, which it approximately is. You might have to worry about what is happening if the instanton is at the border of these subvolumes, but I don't think it is a big deal. Okay. And then we calculate the expectation value of an operator that only lives in the volume 1 and does not have any, none of its spacetime arguments are living in the volume 2. Then what we see is that the path integral factorizes here into these contributions, and the whole thing would factorize if we would have sums and integrals that only depend on delta n1 and sums and integrals that only depend on delta n2 in a factorizing way. And this leads to the following condition on these weights here, which is of course just the functional equation for an exponential. Okay, and then we recover that we have to put in a general phase here, and in general, one cannot explain this phase away. Now let's think what happens if we do this in a situation where we keep delta n fixed. So let's think of a big volume omega 2, and we fix these topologically conserved boundary condition, delta n, on the boundary of omega 2. We can do this in a gauge invariant way. So this is a perfectly sensible theory. And then we have the same structure here. So we have f of delta n. In principle, we could immediately cancel it because it is just topologically conserved, delta n. So this function is the same. But the decisive difference is now that here this delta n2 depends on delta n1 by the constraint of delta n. So at first glance, it looks like they don't factorize. Now let's press on, however, and evaluate these contributions here. And again, we get these modified Bessel functions. Of course, again, we could just cross out this f of delta n. And then if omega 2 is much larger than omega 1, we can again forget about these indices. And in particular, we can forget about the dependence on delta n1. So more precisely, we are summing here over delta n1. And if this volume is small, at some point we're hitting values of delta n1 where this contribution just dies exponentially. So there's a control of the size of this argument delta n1. So we can always choose omega 2 large enough such that this index does not matter. And then we can cancel these guys, we can cancel these guys, And we are left with this expression here. And what this means is that we can calculate our correlation functions in the subvolume. We do not have to fix the winding number. It can flow in and out of the volume. So in that sense, the boundary condition for the winding number is not fixed. So here again, I mentioned that theories with fixed delta n have been studied by Lloyd Wheeler and Smilger in the 1990s. And I think they have found, they have looked at fermion correlations and played it at a different angle, but they also found for massive fermions compliance with cluster decomposition and not any problem in fixing delta n. Now the question is, the last question is there then a choice, if I have these finite volumes, whether I can interfere these volumes or I don't? Because here I sort of fix delta n, and in this calculation on the previous slide, I keep delta n, so at the boundary of omega-2 free, and sum over all this. But then I go back to this argument that I have made, I hope I find it here, on the other correlation functions like endpoint and stress energy and so on, which are calculated in precisely the same way as this 2-point function that I've been talking about. And of course, along the same line, coming back to John's comment, we can also calculate the 2 and f-point functions. They all come with the same phase here. So this phase appears in all correlation functions one time and one time only. And when we calculate the expectation values normalized by the partition function, they just happen to cancel. So I would make the statement here that an observer that is made up of local quantum fields cannot see this interference between these vectors with different delta n, because after all, this observer lives in a world with a fixed delta n with these boundary conditions fixed at infinity. So in that sense, this theory with the theta vacuum, where we sum in infinite volumes over all topological sectors, is equivalent with a theory with a fixed delta n in a large volume. Of course, there's another caveat, just to bring it out of the discussion before it is being mentioned. So if delta n is finite and omega-2 is finite, you will have a residual breaking of parity, which you could in principle measure. But then you have to argue that you can always, for a fixed delta n, choose omega-2 so large that you drop it below all observable levels. So in that sense, in a finite space-time volume, of course, you can prefer a certain winding number. You can prefer positive winding number over negative. That's just what it is. Okay, so here are the conclusions. So in infinite space-time volumes, these interferences that would, in standard calculations, lead to this misalignment of the CP-odd phases between the correlation functions disappear. So there is no CP violation if we order these limits in the right way around. Now, in finite volume, these interferences remain, so I can still calculate these correlation functions, but the question is whether these correlations coming from these interferences can be observed within a local quantum field theory or by an observer that consists itself out of local quantum fields. Good thing is there's then an agreement between the theories in infinite volumes with delta n either free or fixed, as I discussed, and theories that are constructed in large and finite volumes for fixed delta n. So we cannot see, so this problem does not tell us whether we're living in a finite or infinite or periodic volume. And so regarding the last point that I've made, if we look into a subvolume, we can work with free delta n1, free winding number that can flow inside and outside of the volume. But we have to account for the topological conservation of the total delta n, which by choosing omega-2 very large, we can of course drop below the observable levels. Yeah, so that would be it. And thanks for listening with an open mind. And in the spirit of the opening remarks of Daniele, I am looking forward to the discussions that hopefully happen this afternoon and also by email or whatever channel. Thank you.
Thank you, Bjorn, for the nice talk. So yes, I would open the discussion session. So are there any questions? So if so, please speak up. Or any comments? Claudio raised the hand, so please go ahead.
Sorry, maybe I missed the point why you need the infinite volume limit before the sum on topological sector.
Yes, okay. I'm just coming back to this. So it makes a difference because it changes, okay, mathematically it changes the structure of the sum. It is a case of non-commuting limits. And so the mathematical point is just, and it's close to the one, to the physical point, that, that, as I explained, if we take this infinite volume limit first, then essentially all these contributions here, all these factors are the same. And then there are no residual interferences. Whereas if I keep these guys here finite and then do the sum, even if I take this expression here and I sum this expression over all delta n while keeping Vt finite, then I get these interferences. It would just be a bit of more of a complicated computation with the sum of the special functions. So that is why one better goes one step back and writes it again like this, because then it's just an exponential series. And to my knowledge, this calculation here, the sum has first been calculated, and I didn't really see any papers which pick that up again. In this paper by How Instantons Solve the U1 Problem by Toft of 1986, which is very well known.
Yeah, no, that's okay. My point was I didn't understood the last line of this slide. Why you need, I mean, you can do in both way. That's I understand. I didn't get why to do the thermodynamic limit before it's the right way from your point of view.
May I add something here?
Yes, please go ahead.
So,
connection.
at least in an infinite spacetime, when you compute the path integral, you have to sum over configurations with finite action.
Yeah.
And then you are forced then, the classification into topological sectors comes because in order to have finite action, your fields have to approach pure gauge configurations at infinity. And then you do have a classification into topological sectors. That's why the classification into topological sectors makes sense in the infinite volume limit. At finite volume, it's not even necessary to have a classification into topological sectors because all field configurations are allowed and they give a finite action as long as.
Well, that's a possibility. Indeed, there is another one that I would say is less popular, but I think the proposal of this was Jakiv. Instead of looking in the topology of the gauge field, you look at the topology of the gauge group. I mean, this you realize it if you try to do canonical quantization. And then you see that the structure, I mean, the topology emerge, but is not anymore the topology of instantons, but the topology inside the group. And that is there even in finite volume. So I'm not really sure that this is really the correct way of thinking. Even before, because otherwise you'd get zero topological susceptibility doing in that way, or infinite. Now, I'm a little
sorry about that. I've been out.
Yeah, Bjorn is back. Perfect.
It was a hardware crash. I hope it doesn't happen again.
Carlos added some comment meanwhile.
Okay, so Carlos,
okay, so,
safe here.
Okay, I've lost.
Thanks, Carlos, for being here. So I don't know what has been.
So Michele has a question in the chat. Since Bjorn is back, you can answer. So Michele asks, what goes wrong with chiral perturbation theory?
What goes wrong with chiral perturbation?
Theory.
Okay, so the point of view here would be that, I mean, we know that we construct these phases that we have in chiral perturbation theory from this effective Toft operator, yeah? And so I would just replace in this term that one put into the potential for the U1 boson, I would just replace the phase theta by alpha or minus alpha. This is what we would suggest. I think we are descent from the fundamental theory to the effective chiral perturbation theory in the same way as everyone does. And of course, there are all sorts of problems with these calculations, which is precisely why one has to resort eventually to non-perturbative techniques to predict the size of this operator. But just as to see what is the phase here, I think we are making no other approximations than what is standard. In particular, we are treating the theory perturbative when really it is not perturbative. But yeah, in my view, there's nothing that goes wrong with chiral perturbation theory because
no. But my question is, so you're not claiming that is incorrect the chiral rotation that rotates theta to the mass matrix, are you?
No, that's, I mean, I made this comment in my first slide.
So if you assume that, you already see in the chiral Lagrangian that that violates CP. For example, eta goes in 2 pi, and you know, with a little more effort, you also see other things. But so if either you are claiming, I think that you know, the chiral rotation is incorrect. Otherwise, I don't understand how you know, this can be how you can derive a different result in chiral perturbation theory.
Okay, as I said, you can have, the statement is that there's one rephasing invariant, which is theta bar. And this theta bar may or may not show up in observables. And the simple answer to this is that in this infinite volume limit, it is not showing up in any observable. So
this I'm willing to buy. I'm just asking, so I mean, how this would change the computation that do the chiral perturbation theory, which just requires to rotate theta to the mass matrix. Because you're not claiming that is wrong. If I have that, I already know that QCD with theta angle violates CP.
Yeah, but in this present calculation that we are doing, so if we rotate theta to the mass matrix, and so then we just have this phase alpha, and theta is 0 in these final expressions that I have. Let me bring my slides up again. Sorry, they went with the...
No, I understand that you're doing a different computation, which is weakly coupled. Okay? But you're on the other hand claiming that you know, you always don't find CP violation. So a strong coupling, I can do a simpler computation where I see immediately that there is CP violation. So,
well, I don't know whether it's so simple at strong couplings, because the
so if you believe the chiral Lagrangian, that you add masses and you know, usual techniques.
Yes. So what I'm essentially saying is, if so let me just flash up my slide again.
But can I make a comment?
Yeah.
Yeah, go.
I mean, so I think there's some misunderstanding between two. So Michele is saying, just explicitly in the chiral Lagrangian, the usual way we put in theta bar is we put in theta bar purely in the quark mass term, right? And then in the chiral Lagrangian, we know how the quark mass appears. I mean, it's the trace MQ sigma, where sigma is the exponential of the Namber-Goldstone bosons. So the only way you could get rid of that thing is if there was a massless field or extremely light field, much lighter than the QCD scale, that adjusts itself. Of course, this is what Gia sometimes says, that inevitably you have like an axion-like solution. So if it was the case that QCD had an almost massless state that could adjust, then you could adjust the phase and get rid of that. But it doesn't from lattice simulations. So you need to be claiming the lattice simulations are incorrect.
Okay, that is of course a thing that I don't really want to get at length before Claudio's talk. Because I mean, sort of these comments that I made at the end of the, I mean, okay, first of all, I think John said kind of what I tried to say before also about these, how these phases appear in the effective chiral Lagrangian, because we take this here as our effective operators, yeah? And from this, we construct with the standard spurion, etc. arguments our effective chiral Lagrangians. And so if we have theta here, then what shows up in the chiral Lagrangian is theta bar as the rephasing invariant. And if we have minus alpha bar here, then there is all the rephasing invariant CP phases in the effective chiral Lagrangian are 0. So in some sense, we have to come up with an object like this and calculate it in the best way we can to predict from this the chiral Lagrangian we are using. Okay, and as far as a lattice is concerned, I think, okay, I prefer to listen to Claudio Bonatti's talk, of course, but I mean, lattice, but to maybe set a bit of the context why I said this, lattice is, of course, the situation where we have periodic boundary conditions. And as far as I gathered from the literature, if we take the continuum limit on the lattice, we have topological freezing. So the lattice stops to sample over these different topologies. And so, and that's where, of course, my expertise is already overstretched, because some people in the lattice community consider this as a problem. So they get better lattices, which are more close to the continuum limit, but then they don't like or see it as a problem that it stops sampling over the topological sectors. And so it would be interesting to discuss what sort of the spirit behind this is if I sample over the topological sectors in this way. I mean, there are some approaches which choose open boundary conditions here to this volume omega-1, as I understand. And of course, the sampling over topological sectors is automatically if the lattice spacing remains finite. So the question is really, what is the picture behind that people have in mind when they do these computations?
I must admit, I'm very confused, because lattice simulations certainly have the property of cluster decomposition, and the appropriate length scale is lambda QTD. And of course, you know, always lattice groups do simulations with large enough volume, physical volumes, which are much bigger than lambda QTD inverse. So you should recover the infinite volume limit from lattice simulations adequately, because the ratio of length scales, the ratio of their physical volume compared to lambda QCD inverse is sufficiently big.
Yes.
So
I mean,
the only way that can go wrong is if there's very, very light fields, but QCD doesn't have very light fields. That was my point.
Okay. I'm not sure where I disagree or whether I disagree, because I think I'm making the claim here that we can understand the cluster decomposition in this way. So I'm not making a claim that the finite volume does not exhibit cluster decomposition. And of course, I think I would demand of any sensible discussion of this topic that we sort of are insensitive to the question of whether the space-time is infinite or finite. So that is why I particularly added.
Yeah, I totally agree with that. As long as the space-time is larger in volume than lambda QCD inverse to the fourth, right? It has to. That's the appropriate length scale. So, because of course, if we make the space-time very much smaller than that, we know we can exponentially suppress the effect of theta bar. Right, so we're always talking about space-times which are big enough. So I really don't understand how your computations agree with those lattice results, because I think for what you say to be true, you would need a light state.
Why would I need a light state? Because it is an explicit. Are you saying that in our case, the eta prime would be light?
Yes.
Okay, I think, okay, that's something that has been worrying me, but I think that is, I would address by saying that, I mean, in either case, in either setup, we have the problem that there is a conserved current, which is the chiral current plus the topological current. And then I think the usual argument is this like twofold thing that the 't Hooft calculation shows us that there is somehow a loophole to the expectation that a massless boson arises from the violation of this current. And the more to put the finger on where this happens, people often state this Kogut-Susskind pole, so that the theta would be a non-dynamical particle with a zero mass. Yeah, so then they get away with not having a Goldstone boson. But I think, I mean, this is certainly an interesting point, but I don't see that it takes out what we are claiming here immediately, because I think this problem arises in both setups.
Well, I think we should come back to this. I mean, I should read your paper carefully, Bjorn.
Could I add just one clarification,
Carlos,
please? Just wanted to say that this result about finite volume, the theta-dependent dropping out, is only valid if in the large volume you are restricted to be in a single topological sector. The moment you start in the large volume sampling over all the topological sectors at finite volume, you will recover interferences and CP violations.
Carlos, I had a question indeed on this point. So if I understand correctly the issue from the physical point of view, say that I don't care about the infinite volume limit, I don't care about swapping limits, I'm only interested in the finite but large volume. So essentially what you're saying is that if you're looking at an observable that acts on a small portion of volume, say smaller than lambda QCD inverse, then you're not sensitive to the other topological sectors. So you should restrict yourself to the same topological vacuum. You should not sum over them. This is essentially what you're saying physically. Is it correct?
I let Bjorn answer this.
I think.
So this is the whole point from the physical point.
Do you see this equation that is flashed up now?
Yeah.
Yeah, so that's precisely what Daniele just paraphrased. I think if you let these boundary conditions float in and out of your subvolume, then these phases don't appear. Because essentially they cancel because they only make sense if I define them globally at whatever my boundary condition at the outer edge is. And then they always have to cancel.
Okay, so more questions or comments or doubts?
If I can add a comment on this. Well, what you are using, it seems to me that it's just that the infinite volume of the partition function at fixed topological charge is the same for any topological charge. That's it. As a result, that I would say whose physical understanding was something that was already said, that once the volume is larger than the QCD scale, then the local fluctuation balance the thing that you have a global charge fixed. But then the point is that at the beginning of the calculation, you start from looking at this local fluctuation. So if it's at some point you exchange the limit, it's something like having exactly zero topological susceptibility on any volume. So it's.
Yeah, I would agree with that. I think that's correct. Yeah.
Sorry, you're saying
I agree with the comment. I don't know who was speaking, but whoever made that comment, I agree with that. I believe.
Claudio and John agree, basically.
So maybe you can paraphrase this somehow, because I'm not sure whether I understood what you were saying.
Yeah. Well, the point is that if you stay at the approximation that you are doing, basically, is the development of the Bessel function. That is a fact that in this case, for instance, on gas, is the fact that, sorry, when you compute the partition function at fixed topological charge, when you increase the volume, at some point, you reach a value that is independent of the charge that you have fixed.
Okay.
Now, the reason for this is that there is a correlation length that is finite. So when the volume is large enough, there is self-averaging. Different regions of space basically work as if they were open, but they are far enough that you can sum up incoherently on all. So basically, this is the physical reasoning behind the slide that is now shown. The point is that in your computation, you started from the beginning just looking at this local fluctuation. So you first have to sum on that and then perform the limit, because otherwise you are just imposing a hard cutoff at some point on the number of fluctuations that can enter your computation. I mean, at some point here you have the sum up to large n. If you keep large n fixed and you perform the infinite volume limit, you are saying that on average you have zero instantons, zero density of instantons.
I'm saying I have zero winding number density.
waiting
but the density of instantons is
sure, you're right.
What is set here.
Yeah,
so the density of instantons is just given by essentially this alpha here.
Of course, but anyway, even the average of the difference should be different from 0 because there is a topological susceptibility. So you should scale that large n with the square root of the volume, I would say.
Okay. But I mean, the question is, why should I do this really? Because in principle, these pre-vacua are only defined in the infinite volume limit in first place.
Well, that's
so the question is, does it make any sense to look at any of these individual terms without strictly taking the limit to infinity?
Well, that was what I was saying before, but probably you just had some problem with the line. This is a problem when you work in the semi-classical approximation. But if you just work with canonical quantization, then you get a theta dependence even at finite volume.
Well, okay, so this is, okay, maybe I shouldn't say more, but we don't want to run circles, but I'm, of course, saying that in a finite volume, if you fix delta n, then there can't be any dependence on theta, and there isn't. But if we allow to interfere over these thetas, then of course we recover the standard result. So the main question here is whether then it is observable to an observer in terms of local quantum fields.
You know, I understand this. My point is that doing in this way, it seems to me that you don't get a topological susceptibility.
I think I can calculate topological susceptibility also in
if
this
you do
setup.
It exactly in that way, I would say you get or 0 or infinite.
I mean, I think I can use these sort of averages. So essentially, I want to calculate n of 0 times n of x. And I mean, I looked into that. It's a couple of weeks ago, but I think I found a sensible answer for a non-vanishing topological susceptibility. Also in this case, I didn't see a difference. But of course,
is just because if you go in the previous slide, I think it's the
previous.
No, it's the one with the ratio where there is that big N.
Here's the big N appearing.
Yeah. If you want to compute the topological susceptibility, here you should have at numerator delta n square,
okay,
z delta n.
Mm-hmm.
Now, if you try to do the same thing that you did now, all the z delta n factorize, and you get an infinite, I would say.
Okay, I mean, I can...
I think the problem is the way in which it is computed.
I probably can carry out this calculation, but I think here we have seen that if we have these n's here, we are getting essentially the right factors such that these volume dependencies are canceling out. So of course, it's something that I would have.
That's for the average instantons.
Yeah, this is not the susceptibility, but the susceptibility could be computed in a very similar way. And all I'm saying here is that if we had such an n square here and we calculate the expectation value, I think it will also be independent of the volume if you normalize it by the partition function. And if it's I mean, it would go to 0, I guess, then there would be some dependence on the volume. But I mean, of course, this is an aspect that I would be happy to get in touch with you by email so we can exchange these arguments in a more detailed way.
Sure.
Okay, so I would suggest to move on.